Okay, so last time we talked about something having more structure than a graph, which we called map, which was the same as graphs, but we couldn't intersect them. Like you couldn't have overlapping lines. So graph that we draw on a surface so graph we draw on a surface without lifting the pen, and whose faces are isomorphic to disks. So what is isomorphism? Isomorphism is just it's without deforming. Intuitively, it's just deform without changing the actual structure, in the sense that without, what's a better word? You can deform one thing. For example, you can deform a donut into a mug, and so we say the donut and the mug are isomorphic. That is, you can deform one into the other without changing its genus, or genus is basically the number of holes. So that's a way to look at isomorphism. And from a topological point of view, a plane or sphere is like any surface that doesn't have any hole. Any genus 0 surface is the same as a plane or a sphere. That is, they're isomorphic. That is, they are the same. They are something called topologically equivalent. We don't need to know any other stuff. We just need to know that the genus, the thing that we need for RMT is what genus is. That is basically holes. And genus 0 examples are plane, sphere, and let's see, cube. Genus 1, mug, donut, and so on. Genus is basically a whole, like this. Okay. So what was maps again? Maps was, for example, if you have a graph like this, say this is a graph, and this is another point. The overlapping thing allowed in graphs, but not in maps. So this is the only basic difference. Another one is they're isomorphic to disk. They're somewhat equivalent. So there's that. And isomorphic to disks mean you can like deform this. For example, if this is a face, we call this a face of a map. So if we get rid of okay, let me get rid of this. This is now a map. And you can deform and make it into a disk. What you can't what you wouldn't be able to deform is if this was something like this, if this had a hole or a genus, then cannot be deformed into a disk like this. Or if there was, say, say an intersecting line like this. So only in that case you wouldn't be able to deform. Otherwise, in most of the scenarios that we'll deal with, you can deform the faces into disks. That is, you can make them into disks. You can squeeze them and make it into a circular structure. So now the question is, what are the maps we can draw on G equal to 0 surface? So one of the maps, say if this is a G equal to 0 surface, we don't have any holes in it. Let's give it, yeah. This is a map in G equal to 0 surface. We can have faces. For example, these are the faces, F1, F2, F3, F4, and F5. So this is a map on a genus 0 surface. Another map could be on a genus 0 surface would be our figure 8. So how many faces would we have here? Any ideas?
3.
So F1, F2, F3, 3 faces. And all of these faces are isomorphic to faces, disks. All of them are isomorphic to disks. You can take this shape, deform it, and make it into a disk. So let's see an example. Is this a map for a genus 0 case?
No.
Can you say why not?
I mean, the lines are, you can't draw it while keeping the pen down.
Exactly. Or you have intersecting lines. Another way of saying it is they aren't, you can't actually, these aren't isomorphic. The faces aren't isomorphic to disks. There are holes, there are intersections. So, and you cannot make them equal to disks. Okay. But this map, okay, now let's look at the genus 1 scenario, genus 1 surface. So let's take a genus 1 surface. Genus 1 is just a hole with one hole. It's important to remember a genus 1 surface, for any genus 1 surface, can be transformed into, let's say, a mug or a donut. So all of these are equivalent. So let's consider our figure 8 or this diagram. Is this a map for this? Nope. Why not? Because if you take F3, for example, F3 has a hole in it. And can you make it equivalent to a disk? A disk has no holes. It's a genus 0 thing. So it's not. Our figure 8, in this case, is not a map. However, this example, this diagram is a map for genus 1 case. So let me give you an example. Let me show you something. Do you have a mug beside you? Or can you imagine a mug being beside you? And I'll give you a picture on Slack. Okay, let's give it an informal gallery. So since I didn't have a donut beside me, I used a mug and tried to draw this thing on a mug. This is a map on on genus 1 surface. I've uploaded it to Informal Gallery. If you want, you can have a look and see why this is a map. I took a mug and tried to, yeah. So if you want to draw this out here, if you want to draw this out, let's have a genus 1 surface. Let's make it more like this. If you have a genus 1 surface, you can start drawing your map here, and the other side of it, one side of it goes down, circles, and comes back here. Another side of it could be like this. If you're confused, you can have a look at the picture that I posted. You'll understand why there is no intersecting lines and why this is a map. That is, yeah. So have a look at the picture I posted on Slack. You'll understand why this is a map. And so an important thing to notice is, even though this graph wasn't a map in genus 1 case, it is a map for genus 0 case, it is a map for genus 1 case. So some graphs that aren't maps in a certain genus can be a map in a different genus. So we can promote almost all of our graphs to maps. For example, if you remember, when we were calculating expectation values, expectation values of this corresponded to, for example, you had 4 factorial, 1 vertex thing. So this corresponded to 3 diagrams, which were 2 of the figure 8s of different like this. One of them could be like this. Another one was this ring. So these 2 are maps for genus 0 case. This is a map for genus 1 case. So it's just 2 plus 1. It's a genus, 2 of them are genus 0 maps, and 1 of them are genus 1 map. So instead of 3, we have 2 of them for genus 0 and 1 for genus 1, even for 1 vertex. For multiple vertex, you will have different graphs corresponding, or maps corresponding to different genuses. Now let's move on to, let's do some topology. That is, so let's say we have a genus G surface. That is, it can be a mug, it can be of a genus 2 surface, it can be a genus 3 surface. Well, let's say we label the genus by G, and let's say we have V vertices and F faces, and what else did I miss? Edges. E edges. So, and let's define a quantity which we call the Euler characteristic. It's called the Euler characteristic. That is V, we define it like this. It's vertices plus faces minus edges. And we say that, we won't explicitly prove that, but we'll say that X is an invariant quantity, or it's sometimes called a topological. And what do I mean by an invariant quantity? That is, for example, let's say for genus 0, chi, all of the chi's or all of the Euler characteristics same for genus 0 case. For any genus you pick, your Euler characteristic for genus 0, or any surface you pick with genus 0 will have the same Euler characteristic. Genus 1, same Euler characteristic. Genus 2, same. So for each of the genuses, you'll have a fixed Euler characteristic. One way to check is, for example, let's have a look at here. So how many vertices do we have? 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5, 6. So this was so we have 6 vertices. How many edges do we have? 3, 4, 5, 6, 7, 8. How many faces do we have? 5. Let's see. 1, 2, 3, 4, 5, 6. Why am I getting F2, F3, F4, F5? So 5 should be edges. 5 should be vertices. 5, 6 faces.
You have 9 edges, I think.
Yes. Yeah. I have 9 edges. So the Euler characteristic for genus 0 is 2 for this map. Let's see what's it for this map. We have 1 vertex and how many faces do I have? 3. And how many edges do I have?
2 edges.
2. So Euler characteristic is 2. For genus 0 case, we see that any map you draw will have the Euler characteristic will be 2. And for genus 1, if you do the same trick, you'll see that for genus 1, it turns out to be, for genus 0, G equals 0, this turns out to be 2. For genus 1, this is just 0. So we won't go into the details of how we derive this formula, so I'll just state it here because we are not doing a course on Riemann surfaces. But the Euler characteristic in terms of the genus is expressed like this: 2 minus 2g. You can check for different genuses. You can pick an arbitrary genus and check, and you can draw different kinds of maps on it, do some triangulation of any genus surface. Triangulation as in you can discretize any surface, and you'll have vertices, edges, and faces. And however you discretize your surface, for a certain genus, for example, genus 0, the Euler characteristic will be 2. For 1, it will be 0, and so on. So this is the Euler characteristic in terms of the genus. And we won't go into the details of how this doesn't change how this is an invariant, or how we can add many triangulations and see or do those topology stuff. We'll just stick with this formula and try to understand what's going on. If you're interested, we can discuss this later, but for this discussion, let's just stick to this. Okay, so let's say you have 2 surfaces. and you're gluing them. You have two surfaces. Let's say this is genus G, and you have another surface is genus G prime. So what is the total if you glue them? If you attach two um, surfaces like this with different genuses, what is their Euler characteristic? So, or let's give them a new surface name. Let's say G double prime. That's better. It's just the sum of the 2 minus 2. These are the two things we need for our discussion, for when we will be doing ribbon graphs. So what did we learn up to this point? We learned that a map can be described by vertices, edges, and faces. And of course, it depends on which genus surface we are drawing. But when you are calculating maps, it's very easy to calculate vertices. If you write a partition function, it's very easy to calculate vertices. How? You look at the power of G, or genus and G. Let's use G. Okay, G hat. If you look at the power of G hat, that is, if you remember our partition functions, these were something like this. If you look at the different powers of G, for example, if you expand this out, this is 1. That is, you're looking at vertex 1. And how many edges do you have? It depends on the valency. So in this way, you can count the number of vertices and edges, but there is no complete tool to count the number of faces. So we need to develop a tool for edges. So if we have a tool to calculate, if we have a number, or if you have something to keep track of the faces, then it basically solves our problem. Okay. Achha, can someone say how many faces I have here, or in the mug picture I posted on Slack? How many faces do I have there?
1.
Why is it 1?
I mean, it flows through the back. So if you like cut it along the lines that have been drawn, you don't actually separate out any surfaces. They're all connected across because of the handle.
Exactly. So it's just one face.
I actually booted up Blender and made a torus and cut it with Abdullah yesterday, and we saw that it actually has only one face.
Oh, wow. Did you make a video of this?
I could, I guess. I don't have any recording software, but I'll do it.
Okay, can you do it and post it? That will be a good resource. So because in a lot of circumstances, it's very hard to, for example, if you're looking at Mobius strip or things like that, these are very hard to visualize. Because this somewhat deviate from our logical thinking, if you think in that way. So yeah, if you can do it by hand, a lot of people know how to do these things by hand. I personally don't know how to do them, but if you try out yourself, you cutting them out like that and see how many faces you have, so you can understand these things better. Okay, so remember our Euler characteristic was like this, and we defined Euler characteristic to be a quantity like this. So since we want something in terms of the faces, we can write everything in terms of the faces. If we take the vertex number and edge number to that side. So yeah. So now we have to develop a machinery so that we can count the number of faces. Okay. Also remember one thing, when we were drawing, another thing to remember, when we were drawing the X4, these graphs, we had, for example, this corresponded to genus 0 case, and this one corresponded to genus 1 case. And here there was only one face, and here there was only 3 face. So for genus, for one thing to notice is that the same graph, that is this one, gives rise to maps which can be drawn on different genus surfaces, G0 and G1, and they have different number of faces. So this is, keep hold of this, that the same graph, when transformed to map, has different number of faces, and of course in different genuses. So we need a way so that we can keep track of the number of faces. For example, in the same way we keep track of the vertices. So it was the idea of Gerard de Hooft who first came up with the ideas of these fat graphs, or ribbon graphs that we will call them. And in a conventional way, for example, if you are calculating ij, or if you can write it like xi, xj, the propagator is given like this. It's I to j, or whatever you want to label them. This is a vector. If you remember our matrix integrals that we were doing, it was something like this. And the first term was x transpose x, or something like that. So they were vectors. His idea was to transform these vectors into matrices, into a 2-index object. This is a 1-index object, and a matrix is a 2-index object. So his idea was replace vectors by matrices. I'll explain this in a bit, but first let me draw it how he labeled it. For example, if I goes to, let's say, L and so on. It's like this. Before we had a single line propagator, we have a double line thing now. And we represent it by, for example, this will be represented by, yeah, okay, we'll come back to it. For 2-index objects like this, Mij. And if you remember, our graph was something like this. This was our figure 8 graph, which is something like this. And this was our another graph. When we replace it when we carry this on to fat graph technology, or when we make this fat graphs, this will look something like this. We'll have double lines. So this is will look something like this, and you'll have this things coming out, going in, and all those stuff. So this is the double line notation. Previously, our graph was something like this. Now, in the double line notation, since we are getting rid of the vector concept and replacing it by the matrix concept, only in the hope that we can count the number of faces, this graph becomes something like this. And okay, one thing to remember is that each index I runs from 1 to n. So you will have 1, if we label this as I, if we label this as J, you'll have N, N, N. Because each of these can take n values, you'll have n options for each of them. For each of the lines, you will have n options. That is, each of the lines like this, here, you'll have n options. So 1, n, n, n. And here is, you have n options, here n options, here n options. So yeah. And this is a one vertex graph. So you'll have G n cubed. How many faces do we have here? 3. 1, 2, 3. So these double line graphs are a good way to keep track of the number of faces. One, and the second one would look something like this. So this graph in double line notation, or in fat graph notation, looks like this. These are sometimes called fat graphs or ribbon graphs or whatever you want to call them. So what are the number of faces we have? It's only 1. And our power n just is 1. So this number n that we are assigning, the powers of it keep track of the number of faces you have. Okay, so previously, if you remember our x4 case, you had 3 of these graphs. For example, you have this and this guy and this one, and all of them were weighted by G. And now, in this new notation, you have 2 of them weighted by G and N3, and 1 of them with Gn. That is, only 1 face here and 3 faces here. So by transforming them into matrices, what did I just do? I kept the track of the number of faces. That is, I have a new quantity, n, which keeps track of the number of faces I'm dealing with. So instead of vectors, I made them matrices. That's how I'm keeping track of the number of faces. So if you want to see another example, if you have a triangle graph like this, if you transform it to a double line thing, you'll get n for one of them. And again, since you have another one outside, another index outside, you'll have another option, another n options. So you have total n squared options, and the number of faces is 2 faces. Now that we have everything at hand, that is, we can count the number of faces by just looking at the power of n, and n is just the index we're assigning. Before, we were dealing with vectors. We just had a propagator like this, which tells me to go from I to j. Now I have matrices. That is, I have a two index objects. I have two lines instead of a single line. And yeah, so yeah, okay. So if you remember before now we need all this time we were dealing with partition functions. We needed partition functions, and we described graphs with partition functions. That is, we found out different symmetry factors and so on. Now we need a method of for this double line thing. As I said before, we were dealing with matrices, not with variable or vectors. Now we are dealing with matrices. Before, we had something like this. Even for a one variable case, if you remember, we had something like this. You had a figure 8 in the corresponding one, 3g4 factorial. That is, you have three of them. That is, one like this, one like this, another one. Yeah. So now we before we dealt with vectors or even one variable cases. Now we'll be dealing with matrices, so that we can encode our double line graphs by that function, by that partition function. We need a method for that. For that, we will use matrices. That is, we define this like this over a matrix. Previously, it was over a vector or a one variable case. Now we are integrating over matrices. And this matrix is for your reference. Hermitian matrices are, yeah. Or if you want to write out the component in component form. Okay. And since Hermitian means you have complex entries as well. You have basically they are complex entries, except the diagonal ones. You can write it like this. You can write in component form. And where next? Symmetric because for this to hold, they have to be symmetric. Otherwise this won't hold, because if you're transposing it and doing a complex conjugate, you need to get, yeah, xij should be equal to xji, and yij should be equal to minus yji. That's why I'm saying an anti-symmetric and symmetric. You're transposing this, and yeah. Okay, so the measure and okay, uh, and the diagonals are all real, because yeah, otherwise you won't have a Hermitian matrix. So our measure, we can write our measure like this. That is a product of all my diagonal entries and a product of diagonal entries So now the question is, this is how my measure will look like if you write it in component form. That is, if you write in terms of the components of a matrix, if you write it like that, it will look something like this. Now the important question is, how will I fix my partition function? Previously it was minus x squared over 2, and if you're dealing with valent 4 graphs, it was 4 factorial. What will be in case of matrices? In case of matrices, since we want to generate a number, one way to generate a number out of a matrix is taking the trace over a matrix. So it's how this works: trace over m squared 2 plus, if you want, 4 hands coming out of it, or 4 valent 4 graphs, you have to take trace over m to the 4. In our vector case, this was something like this. You had x transpose x, and if you needed m square, you would have x. You'd have 4 of them. To fix the normalization, if you remember previously, our normalization was dx over square root of 2 pi. When we were dealing with matrices or vectors, our normalization was we had to divide by, if you remember, j equal to 0. That is, we set the coupling to 0. Same here, same case here for normalization, or for normalization, you divide this by setting the coupling equal to 0. Now let me explain a bit of how the trace of m square term looks like. Trace of m square is basically m. You can write it like this. This is the trace. So if you write in terms of the components of a matrix, two of them, because they're symmetric. So yeah, symmetric and antisymmetric parts. So you get 2 of them. Now the important thing we want to calculate, ultimately we want to calculate correlation functions or expectation values. In terms of, if you remember, in the single variable case, n equal to 1 case, when we were doing the vector scenario, this was 1 and xy was 0. Now we need to carry this technology to matrices. What will be the matrix scenario? Okay, you can the matrix scenario, let me write out the answer first and then I'll try explaining a bit. But the explicit calculation, I'll try to give you this as a homework, but let me explain this in a bit. First, one way to look at this is you break the matrices Mij into, say, Xij plus. So all you have are components. That is, these are your single variables like before. And another clue would be another one would be, if x and x are the same, they give me 1. If they are different, that is xy, they give me 0. Yes, this. And let me give you another hint of how to compute this. Mij, if they are the same, that is, if ij equals kl, if they are the same, then if you try calculating it, you will get a 0. So these three are your hints on how to compute them. One way is you just break it down. You try to compute the correlation functions individually. You'll have xx and you'll have yy if you break it down, and you'll see that the only way it survives is if they are the conjugates. That is, if mij, that is mij and mkl are conjugates. That conjugates in the sense that Hermitian conjugates. That is, mij dagger equal to mji. Only way they will survive is this. So I'll try to make a homework of this, or if you can solve it, I'll give you an explicit solution. So this is how a propagator or term looks like in case of matrices. Previously, it looked like something like this. If you had XA, XB, it was the inverse matrix AB. In terms of the fat graph, they're all just delta functions. That is, or okay, a small review about delta functions is that if I equals j, then 1, I not equal to j, then 0. That is, if they're the same, that's 1. If they're not, it's 0. And our matrix propagators, okay, it looks something like this. It's just a notation that you can also deal with the inverse notation. Some books use the inverse notation, that is I goes to L and all those things. The main point is the propagator for matrices looks something like this. All we are doing here, we're just carrying the technology of graphs, that is correlation function technology or partition function technology. We are carrying all these things in case of matrices to the case of matrices. If you remember, when we had multiple, for example, if we say we had something like this, if we had too many of them, we used Wick's theorem. In case of matrices, it turns out we can use them. For example, if you expand this out, where's this? If you expand this out, your first term will be 1. Your second term will be correlation function of trace of M4. You don't have the 4 factorial here. Okay. Trace of M4, trace of M8, and so on. So if you want to calculate the first term like this, what you can do is break down the m's and use Wick's theorem. So let's try to use Wick's theorem. Wick's theorem says you have to pair them up, and it's any correlation function of any 2n variables you can write in terms of correlation functions of 2 variables or 2-point correlation functions, and sum over all the possible pairs. MJK, MKL. So we will have 2n minus 1 pairs, that is 2n minus 1 double factorial pairs, that is we will have 3 double factorial pairs, that is 3 pairs. So what are the individual 2-point functions? You can write this in terms of delta functions. If you break them out, it's just 2 delta functions, delta ik delta JJ, and you'll have delta KI, delta LL, plus delta IL, delta JK, delta JI, delta LI, that is, sorry, L, okay, delta IL, first one and last one, JK, JK, JI, first one and last one, second one and the middle one, KL, it should be KL. It should be KL, and so on. Let's first see what numbers we generate here. First, let's try to evaluate the deltas. Delta JJ, they're the same. So I'll generate N, because each J can be 1 to N. So I'll have N possibilities. N, I get an N from here. L can be 1 to N. So again, I get another N. These two are basically the same. So I get another N. So I have here N cubed. Again, similarly, if you evaluate this term explicitly, you'll get another N cubed. So you'll have two N cubes. And if you evaluate this, you'll just get one N. You'll get N. So what is the basic idea here? If you evaluate this, if you evaluate this, you'll get 2n cubed plus n. So if you want to do a pictorial thing, if you want to draw a picture of this, we have replaced single lines by double lines. If it was a single line, it would be something like this. Since now we are dealing with double lines, it looks something like this. I, L, let's label this J, because I is going into L, J, K. So you have three possibilities here. If you remember, this is our x4. You have three possibilities here. That is, this contracts with this, this. Let's draw it. So you have three possibilities here. So if you draw it like this, let's, one of them, and you'll have two similar ones. Remember, we had two figure eights, and they have, all of them have n cubed. That is three faces. Three faces. So my matrix technology works. It tells me a way to count the number of faces. And the second type of diagram that we will generate is something like this. And the number of faces here is just one. And if you do the double line thing, you'll see that you can, one way to look at this is try starting the arrow from any point, and if you see if you can get back to the same point. If you can get back to the same point, you just have one. If you need multiple, for example, if you start an arrow here, you end up here. So this is one n. If you start here, you can end up at the same point, so another n. If you start here and you get back to the same point here, another n. So three n's. You need three n's to describe these diagrams. This diagram. Here you'll see that if you try drawing this, try labeling this, you'll end up with, you'll see that you'll need only one n, that is n1. That is the number of faces of this diagram. So if you break them out, so how many vertices we have? Here we are dealing with only one vertex. So 2G so trace of M4 gives rise, or the first term in our partition function gives rise to three figures, and they correspond to, they have different faces. Two of them have three faces, one of them has one faces. And in this way, we can keep track of the number of faces. So our partition function expansion will have two terms, two things. One, the coupling, the power of the coupling, or the power of G hat, will tell me how many vertices I have, or what vertex diagram I'm looking at. Another one is the power of N. That will tell me how many faces I'm looking at. Okay, let's see what else have we got. Okay, so now this is a good stopping point for discussion on double line diagrams. So let me just summarize a bit what things we need before we start our actual random matrix theory ribbon graphs. So the things that we need, the things that we try to learn here is we replaced the matrices, we replaced the vectors. Let me write it out. Previously, we were dealing with, say, we were dealing with a single variable, or our partition functions were functions of vectors, or they were described by vectors or single variable cases, if you remember. But now our diagrams, these corresponded to, let's say, graphs, and we learned about their symmetry factors, symmetries. We can talk about the symmetries, and we can talk about how the how about different correlation functions. And we talked about different kinds of graphs, 3 vertex, 4 vertex, multiple graphs we can have. We talked about these things when we were dealing with vectors. And now matrices, we came up with the idea of matrices because we need to describe the number of faces. Why do we need faces? Because as we saw, when we promoted to maps, when we promoted our technology from graphs to maps, we needed a function that described the faces. Because in case of maps, not all graphs, for example, at a certain vertex, not all graphs can be transformed into a map in a certain genus surface. It can be a single, a vertex, a graph with one vertex. We saw in a specific example, a graph with one vertex, a single vertex graph of valency 4. The corresponding correspond to 3 different diagrams, and the 3 different diagrams give rise to maps. 3 different graphs give rise to maps of genus 0, maps in genus 0 case, and one map in genus 1 case. So all our graph won't be transformed into maps of certain genus surfaces. They might be different. For that, we needed a technology so that we can carry out the faces, because the faces offer a good way to keep count of which genus surface we are looking at. Because if you remember, face can be turned into 2 minus 2g plus v minus v plus e, and then we can know which genus it corresponds to. And the number of vertex is just found out by looking at the power of our coupling, or g hat. And lastly, we'll talk in more details about these double line graphs when we officially start or formally start our matrix RMT discussions. But for now, I think this is a good point to understand that, a good point to get an intuitive analysis of how my ribbon graphs are constructed and how they might look like. So when we do our calculation of ribbon graphs, they'll correspond to different genuses and so on. And if you could understand this somewhat properly, then you'll be better off when you study, for example, RMT ribbon graphs, so which are basically fat graphs that we talked about here. So I think this is enough for our discussion, and I'll stop the recording.